Now we are staying in the middle of the Kola Peninsula, near the Monchegorsk town. In the first half of the 20th century, the rich copper and nickel ores were discovered here, and the mining and metallurgical complex was built. Due to this, the gigatons of metal dust and gases are deposited on the surrounding territory, which led to the high disturbance of natural ecosystems. Here you can see the industrial wasteland, which is the result of the operation of the copper-nickel smelter and can be considered at the extreme level of the degradation of natural ecosystems.
Here we do the soil sampling from different depths of the pit layers. We collect the samples for the bulk density with a cup. And we also collect the samples for the chemical analysis. This would be useful if we also know the depth of different layers to recalculate the carbon stocks. This soil profile would be called podzol. Podzol, humic and ferric, which would mean that the main soil forming processes is the migration down the profile of organic matter and of iron. So the following horizons could be distinguished. We have a clearly visible A horizon, which is close to 20 centimeters, which is quite deep for the podzols in this area. And this is partly because its location at the bottom part of the slope, so we could expect some migration of substance, of organic matter from the top, but also because of the vegetation. We moved just a little bit from the sea, but I would expect that the climate is a little bit warmer, because we are not in the classical tundra anymore, but something more looking like forest tundra. You see that the trees are quite abundant here, so we have more input of biomass, and this is also a result to the deeper organic horizon. Then we would have E, or alluvial horizon. This is for the first time we see it here in Teribirka. We didn't see it before. So this is also the reason that the organic acids from the vegetation are strong enough to start the podzolic process, and also because the vertical migration here is quite active in comparison to the histosol which we saw before. So this would be the alluvial horizon, and material from here is washed out down the profile. And these are two alluvial horizon, which basically give the name to the soil subtype. This is the BH horizon, so organic matter is accumulated mainly here. It's quite dense. You see it's pretty dark, and we would expect high concentration of organic matter here. Most of the roots reach only this zone. They do not go deeper because most of the nutrients are also accumulated here. So this horizon would be till 60 centimeters. And below we see another B horizon, but mainly with the accumulation of iron, which gives the, say, iron color. It's also quite dense. You see, it's not strictly horizontal, following the sandy material below, and I would say that we have BH horizon till more or less till 60, 65, and the next horizon we probably could refer to it as BF2, which is also quite dense, even more dense than horizon above. And yeah, the horizon between 80 centimeters and 100 meters could be referred as BC. This is the transition to the barren material. And finally, at 1 meter roughly, we have the barren material, which is likely have the fluvial glacial origin in comparison to the material we saw at the previous profiles. The main factor behind the soil diversity would be the mesorelief. The mesorelief and the added effect of the pollution, which results in the degradation of the vegetation. That's why we call it industrial barren. So the vegetation is almost completely gone, and the processes of the erosion, of the transmission of the material, mainly of the topsoil from the top of the hill down the slope to the depressions, results in the classical katina. So here on the top of the hill we see the more or less typical zonal podzolic soil, but zonal podzol, but with a quite narrow top horizon, partly because generally podzols here are not deep, but mainly because it was quite degraded. We almost do not see the top horizon with the organic matter. The very, very shallow, I would say just a couple of centimeters layer, where additional organic matter brought from the remaining vegetation, but again it's miserable. Further, we have the B horizon, which we can recognize with the reddish color, likely from the iron oxygen. And then we have BC horizon, which is the transition to the subsoil, basically to the parent material, and then the parent material mainly of the glacial genesis. This is the second profile down the Katina. We moved to the middle part of the slope, where we expect maximum removal of the top horizon. And in fact, you see that there is almost no top horizon at all. An exclusion could be found here, but this is likely the buried topsoil horizon, which was further covered from the material brought from the top of the hill. So what we see here is still shallow podzol, but strongly eroded. Again, topsoil is gone, probably together with the heavy metals. And that's why the top horizon would be B horizon. The E horizon is also not visible here. And I would say that probably this wall is better to see. So we can see the B horizon or EB horizon up to the 3-5 centimeters, and then again BF horizon with the high iron concentration till 10, maybe 11 centimeters. Then again BC horizon more or less till 20, 21, 22, and then the parent material, which is here represented by the glacial parent materials. So this is the profile number 2, and we keep going down the Katina, and we'll see how the organic matter together with pollutions will start accumulating at the bottom part of the slope. And now we are at the 4th profile. This is the last profile in the Katina in the lowest position. And you can see that here soil profile is completely different even at the level of the soil type. We were talking about the podzols before, or eroded podzols. Here we have the histosol. Basically, we are in the other type of the landscape. We're not at the slope anymore. We are in the wetland, which is in the depression in the mesorelief. And the histosol we see here is similar to those we saw before, near the Tereberka and on the way to Tereberka. However, if at the Tereberka site the atmospheric precipitation was the main source of the water, here the groundwater level is the main reason for the hydromorphic conditions. You can see that already at the 50 centimeters we have the groundwater level. Partly water from the slope also migrates down the slope, down the hill, but mainly the groundwater level here is pretty high. And above, I would propose to identify two layers, and those layers are quite similar in origin. They're all peat, all swamp, but they are different at the level of mineralization, and this also may depend on the excess of oxygen. When we have the more oxygen, the mineralization is higher. So the level starting from the 35 centimeters is more homogeneous, slightly darker, but at the same time the number of the non-mineralized components is very high. However, the level on the top, especially the top 10 centimeters, is more mineralized. What is interesting, we also have the top 5-10 centimeters dark layer, which was likely brought from the hill. This organic material partly was formed here and partly was brought from the hill, and we expect that together with this organic matter also the pollution will migrate. When we measure the nickel and copper concentration here, at this position we expect the highest concentration, with reaching 1 or even more % for nickel. So this is the most polluted area in this landscape, and you can also recognize with the dead wood we can see around. So the conditions for the plants here are the conditions do not allow plants to survive. So we're at the industrial barren, at the highly polluted area where the concentrations of heavy metals is high and at the same time very spatially diverse. So to support bioremediation projects and generally to understand the fundamental processes of pollution distribution, we need to do the spatial screening. So basically we need the map of the pollution with copper and nickel. And to do it, we need some kind of express technologies to be able to measure it fast and with a high frequency and with a high spatial density. This is possible with the smart technologies, non-destructive technologies such as portable XRF. We'll use the Olympus Wanta PXRF, the model adapted for soils. There are also models adapted for the rocks and for the metals, etc. Basically, our main purpose is to screen the bulk concentrations of the multiple metals and to relate it to the geoposition and to the moisture, to the soil type, to many other parameters which could affect heavy metal distribution. We also link it to the digital elevation model which we get from the drone, and altogether this is enough to model and map heavy metal distribution. The exposition time is 30 seconds, so we shall keep it for the 30 seconds stable, and it does the measurements in 3 replicas and then averages the concentration. So what we can see already, that the concentration of nickel and copper are quite high. They are way higher than in natural and in most of urban environments. Okay. Yes. So let's check what do we have. We have ferrum as the most spread element. That's clear because the pods also dominating here, and that's the normal more or less concentration. And okay, this is the nickel. For nickel we have 2500, and the standard deviation is 51, so it's quite accurate. And for copper we have 1200 and the standard deviation 32. So these are the two main pollutants. We also have quite some for the titanium and less for the other elements. So we fix these parameters, but in field screening of the heavy metals can be affected by some environmental conditions. First of all, soil texture and soil moisture. So for the soil texture we will do it further in the lab, but soil moisture is dynamic, and to measure it we use the soil moisture probe, which we can do the express test. So we put it nearby. Okay, press on, and this is 20.4%. Here we also can do it in several replicas. And of course we put the point at the due position. Okay, so this point is here, it's 67.9 north and 32.8 east. So that's more or less enough for one location. Further we just collect the sample and bring it to the lab.
During last decades, scientists are trying to restore this barren territory. And here you can see one of the examples of the studies. These plant communities were established on the mining wastes with alkaline environment. The alkaline environment is needed to neutralize the mobile metal compounds. Here you can see the initial stages of pedogenesis with the accumulation of organic matter in the top level of the alkaline mining wastes. These alkaline materials neutralize the mobile metal compounds and contribute to the sustainable development of artificial ecosystems.
Industrial barrens in Subarctic is a top-level environmental problem which creates multiple risks for environment but also for human health, and that's why revegetation of the industrial barrens is so important. However, there is lack of technology to create ornamental landscapes in such a severe climatic conditions and a severe anthropogenic pressure. On the industrial barren, we've seen the experimental sites with the grassy land cover. However, this is not the only way to revegetate the industrial barren. And the other opportunity is to combine the ornamental plants and the specific technologies for soil construction, which are studied in these experimental sites.
We established our experimental plots on two soil types. It's a peat soil and podzol soil. We used 3 tree species such as birch, alder and rowan, and 2 shrub species. For the landing pit, we used the mix of initial soil, vermiculite lizardite mining wastes, and grains of fine vermiculite. These additives are needed for the neutralization of mobile metal compounds and for the regulation of hydrophysical properties of soil mixtures. During next years we will study the state of vegetation, soil temperature and also chemical properties of soil mixtures, including the content of metals in different chemical fractions.
So this is really an interesting site. So we've been visiting natural environments where we could discover the podzols of the Arctic. They are so amazing. And here we are on a site which is very much influenced by industrial activities and especially the atmospheric pollution and the acidification of the soil, and no plant can grow obviously on this site, and of course erosion is very strong and the metals were also deposited, which means that the whole site is acidic and contaminated with metal, and there is a very important transportation of the metals due to erosion, wind erosion in particular, because winds can be very strong in this region. So this is a huge area, so it's easy to say that it's contaminated and we have to do something, but I think something should be done and it's possible. And Marina has demonstrated that it's possible to have plants growing for a long time, for a long period. So she demonstrated that the sustainable way of remediation is possible. So now the second step, and probably the next, in the future, should be to implement what she has discovered, what she has demonstrated at the site, the whole site, including the several square kilometers which are affected. And so I think it would not be too complicated. It's just a matter of willing and putting some money, but not that too much. And she demonstrated that liming and having plants, it's a possibility to green the soil, to stop the erosion and have something closer to nature. Of course, in the future it won't be as it was before, but the idea is just to trigger the development of the new ecosystem. So I'm pretty sure that something will happen in the future, and it's really necessary. It's really necessary. We need a better environment, as everybody knows.